Hello. I just want to do a small presentation on torque applications, but mainly also on some thoughts that clinicians may have about the effect of a twisted wire or a torque application to the crown of a tooth. So if you look at this little video, if we apply a torquing motion on the crown of a tooth at the, let's say, a wire, we tend to think that the center rotation of the movement will be at the bracket or at the attachment if you use aligners. That's what we think. In reality, when you apply torque on this rectangle as an example, so the torque application in red is point A is here, point B is there. You got a force this way, you got a minus force on the other side. They're equal and opposite. You get the same in green right here. So do these two same actually force couples, as they called, applied at different location on a free body will have the same effect or will have different effect. One way to find out is to calculate from the origin O right here. So we take the corner of the rectangle and we look at the torque application here and the torque application there, and we create what we call location vectors. So this is point A, so that's vector of A. This is point B, this is vector of B. So these vectors here in red are different from those vectors here in green. This one is longer, and this is the way that you calculate a moment. So the moment of at point A of force F, which is right here, and this is minus F, will be the distance, which is the vector RA times F, and B would be the moment the moment will be minus F times RB. So that's the idea of calculating a moment. So you have two moments being applied at looking at from the point O. Same on the green side. So basically the resulting moment, which is moment, I would say total moment, MT, is equal at MA plus MB. All right. So the moment of M, a moment at A times the plus the moment at B, which then you can take the moment MA becomes this, and this becomes that. So it's F times the distance plus minus F times the distance at B. And you can simplify the equation, as you know in mathematics, and the moment becomes the difference between the two vectors times the force F. If you look at a relative vector positioning, you look at RA and RB, you could actually put it this way. The difference between the two is this distance, which is a vector also. So what you have now is D equals the difference between RA and RB vectors. And the conclusion is, when you simplify the equation some more, M equals D times F, and there is no reference to any point of application. It's no point of application. And that applies for a free body, obviously. Because if you had a nail in the point position of O, that would be a fixed body, and that system then is a different system. So it's independent from the point of application. And what happens when we move this concept to orthodontics and you apply a pure couple, such as a twisted wire into a bracket, the tooth usually will rotate around its center of resistance, not around the bracket. So it's very important to understand. And what is the result of that? It's basically that if you put a pure, absolutely pure moment here, in this direction, I think, or in this direction, doesn't really matter. What will happen is you will have this kind of a result where the root will torque the way you want, but you'll also have significant amount of incisal movement, which you may not like. As so. So in part 2, we'll discuss the mechanics on how to change the center rotation to make the center rotation around the incisal edge and eliminate a movement of the crown and only concentrate on the movement of the root, which is called root movement. Thank you.